Hey scholars, this is Mrs. Gregerson, and we're actually covering our very last geometry unit that we're having, and I am pretty excited about it because in geometry we get to do things a lot with shapes, and we actually do apply it later in future math classes. It might not be as intense as what you remember in geometry, but one of the things that you've naturally worked with is called symmetry. Now, when you think of symmetry, you know it means the same on both sides. We had the property of symmetry, or the symmetric property, and that means it was equal on each side of an equation. Well, symmetry is when you take a figure, and if you basically can you divide it in half so that it reflects upon itself. So that way I know, like when you cut a heart out, like right here in this diagram, it has symmetry because this half is the same as that half, and I would fold on that line and it would be symmetric, because it's the same on both sides. We used that a lot when we were kids to make those little Valentine hearts and stuff that you work with. Now, a figure has what's called line symmetry, which means, now it's also called reflectional symmetry, but it just means, can I draw a line down it so it's the same on both sides? Pretty simple. And that line we call the line of symmetry. So here, that's just our line of symmetry. Pretty simple to see. So some figures have it, some don't. Like here in this figure, you have to decide if it has line symmetry. And for those of you who are very visual, you automatically say yes. But now here's my question. It says draw all the lines of symmetry. Well, one that we all see right away goes right here down the middle. And since it's a line, I'm going to put my arrows on it. Can I go the other way? This way. So right away I can see two lines of symmetry. Are there any more lines of symmetry? Hopefully you can see that there's symmetry going from the opposite points here in this figure. We can go here, we can go this way. Alright, so we have those two. Now, are we still have all possible lines of symmetry? Actually, no. How about, could I divide it in half this way? Do I have another line of symmetry right here? In fact, I can do that all the way around my diagram. I'm going to connect the smaller vertices that are opposite of each other. Or you can call like the inverted ones. I don't know how else you want to kind of describe those. But we'll go right here. So really this figure has quite a few lines of symmetry. Let's count them up real quick. Now make sure you don't double count. So let's start here. We have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 lines of symmetry when we work with this. And I can't say this wouldn't be number 9 because that's already counted with number 1. So you can definitely see many lines of symmetry for this figure. Now the next one, you have a scalene right triangle. Is there any way of drawing lines of symmetry so it reflects on itself? And in this case, for a scalene triangle, it's a definite no. Now how about our next figure here? Looking at that, you should see really two very quickly lines of symmetry. So yes, it has line symmetry. So here's one of our lines of symmetry, smack dab down the middle. And I think these are the two that you would see right away. Again, I'm not being real accurate with this, but hopefully you can see where these would go. Now, are there any other lines of symmetry? Yeah, go through diagonal. And you should have one going through diagonally in this way. Now, if I was drawing accurately, they should all be intersecting at the same spot, but you get the idea of where the lines of symmetry should be. Now, how about the next figure? It looks like it's almost like an inverted trapezoid on itself. Yes, it also has line symmetry. Here's our line of symmetry right here. And I have my line of symmetry going this way. Now, are there any other ones? No, this one just only has 2, but you can see that they're symmetric. All right. Let's do the next page here. All right, so on this one right here, we have this typeset letter B. You should be able to say, yes, it is still symmetric, okay? I have a line of symmetry because it can go smack dab through the middle of these, just like this. Now on the next one, I'm actually going to say no. And here's the reason why. If I draw in what appears to be the line of symmetry right here, does those triangles kind of do what? I mean, not triangles, excuse me, I can't even talk today. Stars, pardon me. Those stars, do they reflect on themselves? Do they reflect? No, they don't reflect carefully enough. There's not enough detail. So that's no because of the middle stars. Now, the big figure itself, yes. So remember to look for detail. Now, we have another type of symmetry also, and that's called rotational symmetry, okay? Now, picture a doorknob when you do this, okay? This is kind of how I think when I look at it. All right, so think of picturing a doorknob. And a doorknob, it's going to be centered, all right? Every doorknob is centered, where you can, the ones that turn, that is, centered so you can twist it. And you're actually using with that rotational symmetry. Now, what is rotational symmetry? Rotational symmetry, or radial symmetry, happens if a figure can be rotated about a point by an angle greater than 0 degrees and less than 360, so that the image coincides with the pre-image. What do I mean by image and pre-image? The image is what changes. The pre-image is where you start. So it's really easy to see how it works. Here, look at this square for a moment. If I put that as a doorknob, a square doorknob, when I twist it, when I turn it to open the door, you can see that it rotates about 90 degrees and it would land and look like that exact same figure. I could go 90 degrees more and I would get exactly the same figure. So every time I turn it, like doing a doorknob, twisting it around, you're going to get the same thing. So basically, there's going to have to be some symmetry aligned with this, be able to work with it. Now, some things you only can go 180 degrees in order to get. Let me give you an example of this. If I have a parallelogram, looking at that, you're thinking, there's no way I can have rotational symmetry with that. But if I put this smack dab in the middle, and I turn it 180 degrees, this point's going to land on this one, and you're not going to be able to tell the difference from the original thing. So if I turned it as a doorknob, it would be 180 degrees rotational symmetry. In fact, that has a very specific name. That's called point symmetry. If you have to turn it 180 degrees before it lands on itself, that's called point symmetry. Now, we have what's called an angle of rotational symmetry. It tells us how far we'd have to rotate it. Here in this square, you can tell that I'd have to rotate this angle 90 degrees to get the same figure. If I did the same thing, my angle would be actually a straight angle or a line, and you can see it would have to be 180 degrees. So we know that would be the case. Now, also, notice here, a square has rotational and point symmetry. Point symmetry means you actually have to rotate 180 degrees. Can I rotate this 180 degrees and still land on itself? Yes. So it also would have rotational and specifically point symmetry. Point symmetry is just rotational symmetry for 180 degrees. So you can't have point symmetry unless it has rotational symmetry, so keep it in that mind. How do you find the angle of rotation? Well, it's very easy to get. You just go 360 divided by the number of perfect parts. Okay? So here it would be 4. And so that would be 90 degrees. Now for this one, what are the same things that repeat? The angles. So you'd get your angle of rotation for this one would be 360 divided by 2, and it's gone 180 degrees. So that's the angle of rotational symmetry right here, 180 degrees for this diagram. So make sure you understand how to calculate these. Now I'll help you with this in just a moment. All right, let's go to the next page. It says, tell whether each figure has rotational symmetry and or point symmetry. Remember, no point symmetry unless it is rotational. So if it's going to be both, that's great. But you can't have the other one doing this one. So let's look at this first one. It says, this diagram right here, this set of aligned segments, can I rotate this less than 360 degrees and land on itself? No. Can I rotate it 180 degrees and land on itself? No. So this would be a neither. All right, now the next one we have kind of this, was it the Windows flag, you know, for Microsoft Windows? And if I put my point here in the middle, can I rotate it 180 degrees and land on itself? Yes. So as long as I can do it under 360 degrees, it's rotational. So in this case, yes, it has symmetry, but it's both rotational and point. What is your angle of rotation? Well, that's going to be 360 this time divided by 2, which is 180 degrees. So that's for sure point rotation. Now, on this next one, which is a railroad crossing sign without the R's, if the R's were there, it was not going to work. But you can see, if I do this just real lightly, you can see where I could have definite lines of symmetry. So I do know, so you can rotate it. Can you see how you can go like 90 degrees or so? It divides it up. You also can see there's a point. You can rotate it around. You can go 180 degrees. So this one is both rotational and point. How do I find the angle of rotation? Now again, this is how I think about it. I go, all right, I know it's 360 divided by something. How many perfect kind of parts are there? Well, I have these kind of wedge circles type things. I have 4 of those. So I go 360 divided by 4, and that's 90 degrees. Now let's look at the next one. This is actually a caution, a slow-moving warning vehicle sign. You see a lot of this out in the country because of farm equipment. I grew up seeing this sign way too much in my life. And it's just a warning to be careful. Now, here's the thing. I look at this, and if I rotate about a point, I can easily see I can rotate to get here. But that's not 180 degrees. So this one's just rotational symmetry only. The reason why it's not point symmetry is if I was to rotate this 180 degrees, this point would end up down here, and the triangle part would be on top. And that doesn't make it point. That has to be the exact same thing if I do it 180 degrees. So this one is just rotational symmetry only. My angle of rotation is actually really easy to get. It's 360 divided by, how many perfect corners do I have there? 3. It's 120 degrees. All right, excellent. Let's look at the next one. I have, oh look, a parallelogram. If I go where my 2 diagonals intersect, this one, I can rotate it. But it's also point, because when I rotate it, I have to go 180 degrees to get there. So this one is both. Okay, it has both rotational and point symmetry. And to get it, you just go 360 divided by 2, which is 180 degrees. Now looking at this one, do I have rotational? If I put a point here, can I land on itself before 360? No. So therefore, I wouldn't have point symmetry either. It's neither. All right, we're going to the last thing for symmetry, and then we're going to go on to transformations. It says here, describe the symmetry of each icon. Draw any lines of symmetry. If they're rotational symmetry, give the angle of rotation. So looking at this one, it does have line symmetry, because you can see I can draw lines with it. It does have rotational symmetry, because I can rotate it around. And it has point symmetry. So it really has all 3, because here's where we're going. If I draw my lines of symmetry in, just like this. I'm doing my choo-choo sound. Sorry about that. Those are all your lines of symmetry. Now, that helps us there. We can get all of those. But how in the world do I calculate my angle of rotation? Because my angle of rotation works with my rotational symmetry. Well, think about corners here. Can I go 90 degrees and get the exact same shape? Yes, because I have 4 corners. So to calculate, I go 360 divided by 40 equals 90 degrees. And I know I can go 180 degrees and get the same shape, so that's where I got my point symmetry. All right, now this is just a piece of fruit that I found here off of the internet, just a cross section. Remember the 2-dimensional image of it. And I want to know if this one has the different types of symmetry. Now on this one, it's kind of cool. It has line symmetry. You can see it right away. I literally can go from the point across. Now, this is nature's symmetry, not mine, so I'm not going to be able to probably draw it perfectly. But I can do that from every one of the points. Here, I get all my lines of symmetry. So if you see this, this actually has how many lines? Oops, I forgot one. That'd be a very poor geometry teacher. Notice it goes through the point and then it goes opposite of that into like the little cross section. I have 1, 2, 3, 4, 5, 6, 7 lines of symmetry. So we have that. And it has rotational symmetry. The cool thing is the rotation is actually you should be able to go 7 times around and land on the same thing. So the angle of rotation is going to be 360 divided by 7, which ends up being like 51 3/7 degrees. Now here's the deal. Is there any multiple of 51 3/7 degrees that would give me 180? No, so there is no point symmetry. Because I can't go 180 degrees, because if I go 180 degrees, this point would end up down there, and that does not coincide with itself. All right, so that's it for symmetry, and now we're going to go ahead and talk about transformations.